Greetings, fellow travelers in the quantum continuum. I'm Bailey, your disembodied yet charmingly British master of ceremonies here at Impact Quantum. The podcast where qubits aren't just theoretical, and entanglement isn't a relationship status. Today, we have an absolute corker of a guest, Bert de Jong. He's not only a senior scientist at Berkeley Lab, yes, that Berkeley, but also the director of the Quantum Systems Accelerator, part of the U.S. Department of Energy's National Quantum Initiative. Translation: he's the bloke helping push the boundaries of quantum computing and sensing while the rest of us are still trying to figure out how to update our Wi-Fi routers. From gravitational sensing with atoms to real-time power grid monitoring, Bert's work is less science fiction and more science, faster than you think. So whether you're quantum curious or just quantum confused, you're in for a treat. Now, without further ado, let's beam into the conversation already in progress with hosts Frank La, Vigne and Candace Gillhooley, and the man who makes qubits quiver, Bert de Jong.
All right. Hello and welcome back to Impact Quantum, the podcast where we explore the emergent ecosystem and field of quantum computing, where it's not just for physicists anymore, it's also for the quantum curious. And with me, as always, is the most quantum curious person I know, Candace Gillhooley. How's it going, Candace?
It's great, Frank. Thank you again. I'm very excited about today.
Yes, we have an amazing guest here. I'm just looking at his LinkedIn about page, and it's a lot. So I should ask AI to summarize it, but welcome to the show. We have Bert de Jong, which hopefully I pronounced that right. He is a driven, strategically thinking leader and team builder, leading with impact and building next-generation leaders. He's a senior scientist at Berkeley Lab and is currently serving as the department head for computational sciences and the interim lead for the Applied Computing for Scientific Discovery Group, ACSD. ACSD advances scientific computing by developing and enhancing applications in key disciplines, as well as developing tools and libraries for addressing general problems in computational science. Wow, there's a lot there. So let's. But one of the things here is that you're part of the National Quantum Initiative.
Yes.
And you're at Berkeley University, the Berkeley University. So that's pretty cool. Continue. Tell us what you're up to these days.
Yeah. Thanks, Frank. Thanks, Candace, for having me. To give it a short on the quantum side, so I lead a large number of programs on the quantum in quantum at Lawrence Berkeley National Lab. So I'm the director of the Quantum Systems Accelerator, which is one of the 5 National Quantum Initiative centers funded out of the Department of Energy. And these are large centers. We have about 15 institutions and about 450 researchers working closely together to really try and move the field of quantum information science, effectively quantum computing and quantum sensing forward, because we see the potential for the nation to be a leader in this field and continue to be a leader for the foreseeable future.
Interesting. You mentioned quantum sensing, and quantum sensing is something that's been kind of off the side of my radar. But when I was at the Quantum Tech USA event, quantum sensing was a very hot topic. What is quantum sensing?
Unlike classical sensing, we're just doing sensing with quantum information. And so I'll give you a couple of examples. This is some work that actually came out of our center where we actually use atoms to sense gravity. So that's a good example. Why is this important? Why did we work on it? Well, right now, if you do these kind of things, you have to use sensors that are kilometers apart. By doing quantum sensing and using the power of entanglement, you can actually make sensors that are going to be millimeters in size, extremely small. Now that changes the game on how you can actually use sensing in many, many different applications. Think right now we have satellites trying to measure gravitational behavior. They get their positions, their GPS is impacted by gravitational behavior. So that's one way you can think of sensing. Fundamentally, sensing, we're trying to figure out really where we could go with applications. We can, of course, use quantum sensors to sense what's happening with quantum systems. So we better understand, for example, what happens in biological environments. Those are quantum processes on its own. So can we use sensors, quantum entanglement as a sensor to probe these kinds of systems more accurately? But there is even more creative ideas that people are starting to think about. Could we do this in a larger scale? Could we use quantum sensing to detect if something is broken and goes wrong in an electric grid? Could we get real-time feedback? Now, those are far-fetched ideas, right? Those are not things that are happening right now. But those are some of the applications you can think of when it comes to quantum sensing.
So this isn't just about, hey, we want to find an oil deposit or a natural gas deposit.
That would be a potentially other direction to think. Let's say you're looking for rare earths, for example, critical materials right now. Detecting those in the ground is not trivial. So, but if you can use a signature, a quantum signature, for example, you might be able to detect deposits. I'm not familiar enough with thinking about this in the oil and gas sense, but yeah. So I would say the differences in densities is potentially something that you could use as a way to do some quantum sensing.
Interesting. The reason why I mentioned it is because I remember hearing about the first time I heard about quantum sensing was looking for natural resources, whether it was oil, gas, or various types of minerals.
Yes.
Which I think would be an interesting use case. But I like the idea of being able to understand what's happening in the power grid, because as we record this today, I don't know if the power is back on in Spain and Portugal.
Oh yeah, I heard about that today. They have no power. Like 50 million people without power.
That's crazy.
Well, I had not heard that,
No.
but that is a major issue. And of course, we've seen the blackouts here in California. Well, we've seen them also in the north and in the east. So being able to respond quicker is always going to be a big challenge, right? And these are large, complex systems, and single points of failure are everywhere.
Yeah. No, that's a good point. And the other thing was, I also heard the term quantum radar, which was another kind of use. So in terms of being able to detect drones, smaller objects flying around, stealth aircraft and things like that. So I think quantum sensing is definitely, I think, going to be one of those fields that, for good or for bad, is going to have a big renaissance one way or the other.
It just seems that quantum sensing can touch on so many different things, right?
Yeah.
Like we're talking about, you were talking about oil and gas. We're talking about, how you can measure gravity, time, acceleration. Like there's just so many aspects. Maybe quantum sensing is more of a bridge. That could be like a bridge technology that could, drive a broader spectrum of quantum technologies because it's effective in all of them. I mean, it seems we've been dying to talk to someone about quantum sensing because it's so vitally important. So now it feels like, we got someone here, like specifically, what fields are you working on in the quantum sensing sense? Like what are you focusing on? National security? Are you focusing on medical implications, natural resources? What are you guys looking at?
So again, we as a center, we really have focused on actually finding ways to harness the entanglement so that we can and build the foundations. Yes, the field is progressing, and I would think it probably is one of those technologies that will be the earliest to market relative to computing or networking, simply because over the last 5 to 10 years, I would say the last decade, the technology really has moved forward to a point that sensing is not that far out. We know how to entangle photons. We know how to entangle the key pieces and actually then be able to very accurately measure these kind of quantum systems and measure the entanglement that allow us to actually make decisions and actually get insights that we're looking for. So it is early, but more and more industries are, especially even quantum computing industries, are diversifying their portfolio. One of the jokes that I always make is for example, if you make a good qubit, it's a terrible sensor. If you have a terrible qubit, they're actually excellent sensors.
Oh, because of the noise.
Yes. If they're sensitive to noise, right? If they can detect the smallest amount of noise, then they are good for sensors. And that's
makes
the hard
sense.
part.
Okay. All right. So all this work and the chandeliers and all that stuff that they do to shield it out, you actually kind of want that in a sense.
Yes. You kind of work in two directions. Exactly. Quantum computers want to get rid of the noise and be less and less sensitive to noise, while quantum sensors want to be more and more sensitive to noise. It's that interesting dichotomy, but that it also means that if you start thinking about, for us, we are not just building quantum computers, for example, with atoms. We're also trying to measure them more and more accurately. And so the more accurately you measure, the more you get sensitive to noise, right? The extra little piece of noise that you didn't know about. That then makes you also better as a sensor. So it's kind of that, even though we're developing technologies for quantum, they have that angle of actually being able to readily used in a quantum sensing realm, just in a different way.
Interesting.
And also, as the sensors, I don't know if it's as important, but as the sensors become more sensitive, like you can go smaller and smaller and smaller.
Mm-hmm.
I don't know if that's necessarily something that is important to this field, but it makes me think when something is sensitive, everyone likes when things can get smaller and smaller.
Well, it has to be, right? So let's say I can build right now a sensor that it takes up a big room in a building. Now, if you want to have that sensor, for example, on a ship or in a submarine, right, or on a plane, you need to minimize it. You need to make it smaller. Or if you want to put it in space, lighter weight, smaller is good, right? So miniaturization, that's what I would say our technology advances have been around. If you look at the first kind of space missions, right, Apollo missions, they had computers that were bytes, not kilobytes, bytes, and they were big. Right now, what we have there, we can do in not even a pinky. It's just going to be a very small square of space. And so miniaturization allows you to scale, but actually, more we miniaturize, we more and more get closer to the quantum realm, right? Quantum is at the smallest scale. So the smaller you make things, the closer you get to the quantum realm, and you start to deal with the same problems that we're dealing with right now when it comes to quantum computing or quantum sensing.
Sensing the invisible and measuring the immeasurable. It's like, you know, it's
I often
exciting.
think of Star Trek, right? Like they pull out the tricorder, which is like a handheld device, and they can tell everything from, medical issues to planetary or cosmic like stuff all in the palm of their hand. And it's right now that's still science fiction, but I mean, I can easily see there being uses for it because, in the TV show, there was always a use for it. So I can, I can imagine, you know, that would,
Well, so think of everybody, well, not everybody, but a lot of people are wearing watches right now, where they
right,
detect heartbeat, blood pressure, all of that, even oxygen levels. And so
True.
that is also a demonstration of new sensing technologies. Um, and they're using light.
right,
Light is also photons are the smallest piece you can deal with. So it's all of that miniaturization and putting together more and more foundational knowledge around how materials behave, how photons, how electrons behave, um, allow us to miniaturize. And all of those phenomena tend to be quantum. And so the
right.
smaller we go, the more we need to actually handle quantum information sciences in general.
Interesting. Um, I would also imagine quantum sensing would help in error correction with qubits, or no? Am I not thinking right?
Um, I uh, I would have to think through that, but I don't think the way we are doing quantum error correction right now would be directly a sensing thing.
Okay.
It's more indirect, but yes.
Okay. Sorry, Candace, looked like you had a question.
No, no, I was just kind of thinking, that, in my head again, because we were talking about the watches and the medicine, just what, you know, it's so the next step of what this could do for people with everyday health issues that they're monitoring. And I don't know, I'm very excited about the medical breakthroughs because you keep on seeing how these everyday devices are now being used by all kinds of people. Like, I think about my mom who was so upset about the cell phone. She's like, I wasn't made for the cell phone, Candy. She's like, I'm 80 years old. Like, I cannot handle the cell phone. I'm like, you can, Mom. Like, I swear you can. And now I watch her take the cell phone and put it to her arm to detect her like her diabetes rating, and then how everything is all interconnected now to help her. When it wasn't like that even a couple years ago. And so I'm seeing how, with medical technology, it's going faster and faster. And I can see how, as the world is having issue with natural resources, that's going to go faster. And of course, with security, national security, that's going to be, one of the biggest ways they're going to want to deal with sensors and stuff. So I think it's such an incredibly exciting field to investigate and for people to figure out how they get to be a part of it
Yeah,
because it's
so I'll
growth.
give you one early sense. So we already using quantum in our medical fields, right? So the MRI, many of us have had MRIs
Hmm.
driven by quantum. It's a quantum technology.
I didn't know that, to be honest with
So
you.
That's
it's
true. I was
I
thinking
didn't know that.
functional MRI, the magnetic one.
yeah,
Hmm.
Yeah, interesting.
So we're already using it.
yep.
So then why
Actually,
are
we use
people
it
so
everywhere. Honestly,
right?
quantum is everywhere right now. MRI is one, but the fact that we have light bulbs is definitely also a quantum phenomena, especially the lights. GPS is driven by atomic clocks. So if we measure atomic systems more accurately, we build better atomic clocks. We have better GPS. Um, think of optical fibers in telecom. We are using photons right now, but could we actually use entangled photons in the future to maybe get better quantum networks? I already mentioned the transistors getting smaller and smaller, needing quantum. So it's there in every way, shape, or form. So yes.
So it
Interesting.
shouldn't be such an argument that's going on, or I should say lively debate, in terms of how many years it's going to take for us to be able to, enjoy, what's going on as more and more breakthroughs are happening. Like, it's already happening. Like, on the show, we spoke with a lovely lady, Anna White of Hitomatch. They're currently using a quantum algorithm um, in their business. We've spoken to, Quantum Night, who's already, coming up with national security measures that are working with quantum. And and quantum encryption. So like things are already happening. We don't have to necessarily wait 5 or 10 years. It's just going to continue to see the evolution as more funding is put behind the science.
Yes, no, we are definitely progressing, but so when you look at where we are and how we've evolved in the last 5, I would say 10 years, we are really trying to push what I coined as kind of the second quantum revolution. And yes, census is one. Networking is a very different challenge, and that's mainly driven by security because yes, we could potentially break information encryption, and then quantum computing. And are they all going to be now? No. Are they all moving forward? Most definitely. Um, and they all have a timeline where I think, depending on how you look at it, I still think quantum computing can have some early impact in the next 3 to 5 years. Um, Now, is
Well, it
it going
seems
to
like it
be a
kind of
quantum?
does now. I'm
Huh?
sorry. Go ahead. Go ahead.
Okay.
Go ahead. I won't continue your thought.
No, it's not like honestly, in the next 5 years, a quantum computer probably will not break quantum encryption and break all the and gets access to all your secret information you might have. Um, but there is going to be a lot of domain areas and a lot of application areas where early demonstrations of quantum computers or even quantum networking will have an impact. We know that banks are actively pursuing their secure networking effectively right now. Surprisingly, not so surprisingly, but it's still interesting. There's a lot of banking companies, for example, that are trying to understand how they can use quantum computing at this point in time. And for them, it's very simple. If you're the first one or you're the fastest when it comes to making decisions on what stocks to trade, for example, you make more money. So everything here in that world is driven by being the fastest, the first. I would say a lot of other technology, a lot of other industries are really looking at, I would say primarily right now, quantum computing as a potential to accelerate their R&D efforts. But that one, as I said, it's going to be very specific areas that where that technology, quantum computing technology, will actually help them accelerate their R&D. It's not going to be across all industries. Quantum computing is good for certain things. It will not be a universal replacement for classical computing in the future.
What do you think is some of the biggest, what do you think are the barriers right now? Like we've talked about the ecosystem. Frank and I discuss this usually with every guest that we've had, that we talk about, the ecosystem, everything from, the physicists and the academics to the commercial practitioners who are, who are trying to be, the business folk that are putting quantum out there to the world, and how there's a little bit of a chasm between both sides, especially when information is coming out from the commercial side, or because academia is trying to make sure that everything that's being said is completely true and practical, and sometimes there's a little bit of a gap between that, and there's a little bit of a chasm where I think it'd be better if there was a bridge between the two sides. I'm also of the mentality that I don't want a one winner take all. I would like there to be like a leader for every type of qubit, that there is another company, because if one company is dedicated to the, ionization, another one is dedicated, to the photons, or to different qubits, then we could have really some of the best technology possible for everybody. But do you see it as a little bit of a chasm in the ecosystem, that there's kind of a little disconnect that's happening between the two sides? Or no, do you think that the two sides are kind of beginning to work with each other?
I think the community is getting better and better at working together. I do agree that one of the big challenges that we are right now when it comes to the quantum ecosystem is that there is still a lot of directions quantum information science or quantum computing can take at this point in time. There is a lot of different platforms that are being developed as we get better and better understanding, better and better control of what qubits can and cannot do. It's not that far and different from where classical computing was for a long time. We had, for a long time, very different technologies. Hey, we moved from the abacus to tubes to effectively transistors. And now there's new types of transistors that are being developed if they want to scale smaller and smaller. I don't think we are much further when it comes to the quantum technologies right now. We have that choice of which technologies will be the best ones. And I think the real question becomes, what are these technologies the best for? And I would argue that there is potential that some technologies will be better for certain application areas, for certain industries versus others. And again, universal quantum computer, sure, we can build one eventually, but is it going to be the best for some of the applications? I don't know. If you look at classical computing right now, we had x86 for the longest time. Now we have GPUs, we have FPGAs, we have new types of technologies that are being developed on the classical computing side too. What you see is a merger from diversity to or specialization to universal to back now a diverse set of technologies that is specialized for certain application areas. I would expect that diversity and specialization to be the case for a while when it comes to the quantum technologies, till we get a couple of that are going to be clear winners. And honestly, we have some technologies that are at the forefront right now. There is a lot of dark horses out there still, right? And so who knows that what we're looking at right now when it comes to quantum technologies, quantum computing technologies, are the ones that are going to be the ones that are going to drive most of the industry. But the matter is the matter of quantum information is a complex matter for industry in general to deal with. And so they need to get an early handle on it. Hey, if they have to still use a computer build of tubes to do their work right now and understand how quantum could actually impact their end user application, their domain, so be it. Eventually, they will transition like everybody else to the technologies that will be most suited for them for their application area or for their industry.
Right. And you mentioned a couple times quantum information science. I think I know what that means, but can you dive deep into that?
So pretty much everything that we've talked about so far is part of quantum information sciences. Fundamentally, we need to understand and fully grasp what the power is of quantum information, what the power is of quantum, and that umbrella is called quantum information sciences. So this ranges from actually doing understanding the physics to actually doing the engineering to actually doing things like quantum error correction, doing fundamental computer science theory effectively, which is a lot what quantum error correction is, to understand how we can harness a technology. But even fundamentally, better understanding what actually quantum mechanics is, how it works, what entanglement actually means, what it means to actually have a statistical process instead of a deterministic process, are things that need to be, that are continuously being studied, probed, and better understood. That's the umbrella of quantum information sciences, is literally that, understanding from the fundamentals to actually getting to a point where we can build systems and engineer systems and then potentially do real applications with them.
So this would be kind of, like information theory from Claude Shannon and things like that. Like, you go from, this is how you represent information in terms of how do you quantify it, how do you measure it, that sort of thing. Is that what you mean? But like the quantum version of it.
Okay. The quantum version of it, yes.
Interesting. And that's partly how I guess that's how Shor's algorithm or Grover's algorithm was worked out, right? Kind of on a whiteboard, so to speak.
Yes.
And like just working with the theory of it before there was the actual hardware, which that just boggles my mind, right? Like that you can think this through.
So let me ask you this. So I'm as you're talking, I'm like doing a little like researching behind the scene here. So they're saying here in classical information, imagine a pianist playing one note at a time. Each note is clear and separate, like a classic bit being 0 or 1. But in quantum information, imagine a full orchestra where every instrument plays every note at once, but in perfect harmony. This is like a qubit, which can be a 0 or 1 simultaneously superposition. And some instruments are linked, so if one changes, the others can change instantly, therefore entanglement.
That's a very simple, interesting description of doing it. So I would say this is the fun part, of course, then. So you're saying this is like an orchestra, but each instrument playing the right and exact right role. Well, that's what we're trying to get to. When it comes to quantum computing or quantum networking right now, there's a lot of noise in these systems. So some of these instruments might be slightly out of tune.
This is why I like.
And so how do we better tune them and make sure that the high room temperature is not getting them out of tune over time, for example?
Yeah. Do you think that the factor you need to get these really isolated systems and down to almost absolute zero, you think that's been a blocker for more of this, or is that just that'll get worked out at some point?
That's an engineering problem, I would say, that
Right.
has been worked out pretty well so far. What we do see is that so the superconducting qubits, for example, are extremely cold. Actually, the fridges we have, right, that we take superconducting qubits in to and then do these quantum processes on with, they're actually colder than the universe. So we're trying to beat what the universe can do to some extent.
Right.
And so, but we're also seeing this now in the other technologies. So our center, for example, has trapped ions and neutral atoms. Neutral atoms, they're now also going cryo simply because they want to get rid of a lot of background noise. And to do that, cryo is one pair. Cryo means we're just going cold, right? So, but it's hard. Honestly, we can build very good qubits, as good as nature will allow them, as long as we don't touch them, right? So the best qubits are the ones that we cannot touch. But
someone had mentioned that. Someone we spoke to talked about and then if you touch it, it destroys it almost. Like it doesn't work. And I just was having a hard time kind of conceptualizing that in my mind about these qubits that you
doesn't have to be the case, right? So a qubit we can build, and if we don't touch it, it probably is staying around for a long time. Now, of course, it's still in an environment. Any stray photon, any ray coming out of the cosmos could still impact the system. So perfect isolation still doesn't exist. Now, there is some technologies that people are developing, like topological qubits, where inherently they would be protected against a lot of these background noises. But in the long run, we want to do something with these qubits, right? We want to operate on them. We want to do something with them. To do that, we actually become part of that noise. We are the noise. If we don't do it exact, don't rotate the qubit exactly the way we think it does, we introduce noise. If we don't do a sharp enough pulse, or we do a slightly different frequency, we are not directly doing what we're thinking we're doing, so we're introducing noise. The other thing is, again, entangling two of these protected or best protected qubits breaks a lot of the symmetries, breaks some of the protection symmetry, for example. So that opens them up again to noise. So the game when it comes to quantum computing is finding a way to control the noise, mitigate the noise to a point that we can then do quantum error correction on top of that. And reality is we are already doing this in classical computing too. Your memory is error corrected in your computer. Chips have inherent error correction. And how do they do that? They just have multiple versions of it, and they just do a majority vote to decide which one is correct. It's not that different right now when it comes to quantum error correction. We're doing very similar approaches where you start to think about how we can do repetition codes effectively. So repeated encoding so that we can kind of decide what is the right answer at some point. So
interesting.
Yeah.
It boggles the mind because, like, you're right. Like, I don't even think computer science undergrads today even cover error correction. And I remember my professor when I was in school said, "Nah, you're probably never going to really see this in the real world," when he was teaching it. I'm like, yeah. This is large. At the time, his words were something to the effect of, "This is largely a solved problem."
For classical computing, I think it
Yeah.
is a solved problem. It's simple. You can do repetition codes.
Right.
I spent 15 years in high performance computing prior to getting a lot more engaged with quantum computing specifically. And we were doing that on the algorithmic side even. It's just replication and being able to make decisions as to when something goes corrupt, if it's corrupt, and how you can correct it at that point in time. And
Right.
so quantum, to some extent, has a similar kind of flavor to that right now, where we use inherently things that look like repetition codes, not in a classical sense where we just make 5 copies of the same thing, but rather store that information in a bunch of qubits and then try to use the entanglement information to decide if a certain qubit is wrong. But fundamentally, the ideas are the same. The approach using entanglement and storing information in a different way across qubits allows us to do things that you couldn't do on a classical computer, for example, when it comes to error correction.
So I would say right now, given what you know and what you do and what's going on in the ecosystem, what is not, I always feel that communication is a problem. You know, those that know, and those that don't know what they don't know. And communication can always be better. So, what do you think those in the know in quantum could do to be communicating, the importance, the excitement, of what's going on in quantum to get more folks, interested so that, either they want to become knowledgeable themselves or that they're going to make sure that their kids are going to do better in math so that their kids can go into a gigantic array of jobs that don't even exist right now, but are going to exist within, 5-10 years. So what do you think could be done better for communication?
Well, that is also a little bit of a twofold thing. So one of the big challenges with a lot of the communication early on had been that it became a hype. And the hype and then not delivering becomes a kind of a valley of death in the long run. It's not going to go anywhere. So communication has to be done in a very balanced way where we need to talk about reality while talking about the excitement and the potentials. But of course, we have a lot of industry right now that have a lot of VC capital that need to deliver, and the danger that not just in quantum, by the way, but also I would say in AI has come across is that there might be sometimes a little bit too much hype. It has gotten a lot better in quantum. There was a lot more hype now, I would say 5 years ago than there is now. And that's a big, good step. But how to communicate excitement to the right people is a big challenge. And it's something that we have focused also on in our center. We've developed programs to actually try to get the excitement about quantum for high schoolers. Looking at going even back to earlier in the K to 12 ranges, because we need to get them excited to go into a STEM field that allows us to get even AA or bachelor's degrees that can build these systems in the future. And you mentioned 5 to 10 years out. No, it's not 5 to 10 years out. It's now. Companies are building systems. They're installing systems at their customers. That's a skill set that doesn't require physicists. That are electrical engineers doing the cabling, making sure the fridges are working properly, the network is installed properly, the lasers are aligned properly. That's a very different skill set that companies are looking for right now. And then that's the hardware, but we need software. We need the nice, simple interface for the end user. And so we need software engineers that they don't need to be experts in quantum, but they need to be able to understand enough so they can build a software infrastructure that is needed to run industrial applications in the future. And the future is sooner, 3 to 5 years. For some applications, not for everyone.
And to be clear, we didn't pay you to say that, because that's what Candace and I were talking about when we relaunched the show. Was somebody had said, someone very smart had said something to the effect: there's enough theoretical physicists in this field already. What we need are the salespeople. We need the marketers. We need every profession that you mentioned, and then some. Right? It's gonna. I hate the term "it takes a village," but it's gonna take a village.
Yeah.
Right? It takes a large village. And I've seen that. I've visited some companies, and it's interesting to see their changing mindset from being physics experiments to starting to deliver early systems to their end users. And it's just a different type of marketing. You need people that can provide support, consulting to the people that are not as knowledgeable but want to explore these quantum systems for their applications. And then there is a lot of application development that has to be done in the long run at the end. It's like, think of if I want to build a better catalyst, I need to have codes effectively that can run the simulations that I need to run. Well, that's not a trivial thing right now. It's like you're still programming in assembly language, and that's not what most people want to do. So even that level, there's a lot of computer scientists and computer engineers that we need for those kind of activities to make sure that the industry is ready for those kind of use cases.
Right. Now that's a good point. I think that it's always good when you hear someone else agree with you what you're but it looks like Candace had a question.
No, I honestly, I was just going to say, I've enjoyed so much what we've talked about. Like, there's
Absolutely.
so many follow-ups that I'm going to have that I'm going to have to convince you to come back onto the show again. In a little bit of time, I'll give you a break for a little bit, but then come back because I just want to delve a little deeper into some of the, you're really on the pulse of where this has to grow, and you have a very unique perspective with all of your experience. You're fascinating. Thank you so much for all of this. I've loved it. That's what I was thinking, Bert. That's what I was thinking, Frank.
Awesome, awesome. Yeah, I want to be respectful of your time but this has been an enlightening conversation. It's definitely it's interesting to think about how organizations have to start thinking in terms of quantum algorithms, even if they don't have a machine yet, even if they don't have access to the chips and whatnot, and if anyone does, right? But I think it's important to start thinking about how to think differently today, right? Because when this happens, and again, that timeline is anyone's guess, those who think ahead of the curve will be definitely in a more competitive advantage. So I actually had to write a trip report in regards to, to me attending this quantum conference, right? And it was kind of like, well, what's the impact to, my day job as a Red Hat? Like, well, right now, this is really from the way I see it. Again, this is Frank speaking, not the company. This is an over the horizon technology from the point of view of the software company. So the best thing to do today is, just kind of familiarize yourself with the concepts, and so that way, when it does come over the horizon, you're going to be in a much better position to adapt to the new situation on the ground. That's kind of that was my elevator pitch.
Now, I would argue from the perspective that I think it already is appearing on the horizon. So I think even those companies really should be careful not to fall behind. And those quantum technology companies that are out there have recognized that and are starting to develop their own kind of infrastructures. And like we had in the classical world, computing
Right.
world, everybody had their own operating system effectively. Of course, eventually, most of it is now run on some version of Linux, right?
Right.
Which Red Hat supports. But I think we're a long ways away to getting in that direction when it comes to quantum, for example.
Yeah, that's fair. That's fair.
But it's needed, I think, sooner than you think.
I like that. Any parting thoughts, Candace?
I like the sooner than you think.
I do. I want to get
I
that on
really
a
like it.
bumper sticker.
Yeah, I do. I do. I think that there's a lot of companies that are putting a lot behind this, and many of them are still in stealth.
Yep.
And everyone's working towards, who's going to break out with the first of something, of which qubit or whatever, or which technology it's going to affect. But I think that just talking to people like Bert, talking to other people that we've brought onto this podcast is really keeping everybody as informed as we possibly can be.
Right.
And, I'm a big believer in the communication. So,
Awesome.
Yes.
All right. And we'll let sorry, go ahead. Any parting thoughts where folks can find out more about you and your research?
If people are interested in learning more about some of the research, I would say go take a look and just look up Quantum Systems Accelerator. You'll find all the information about all the awesome stuff that our center has done when it comes to advancing quantum computing and quantum sensing technologies, from the fundamentals to actually engineering systems. And generally, LBL has some great information about all the research that they do, because the Quantum System Accelerator is not the only one. We have also an advanced quantum testbed, which, by the way, industry can access if they really want to explore quantum and see if their applications could run on those kinds of systems. So there is a lot of different avenues, I think, for industry, for example, to engage with national labs. And of course, I'm representing the national labs here in this conversation. And I think industry should really carefully look at the opportunities that could afford them.
Excellent. And with that, we'll let our AI finish the show.
And there you have it, dear listeners, another episode of Impact Quantum wrapped up tighter than a qubit in a cryostat. Our thanks to the marvelous Bert de Jong for transporting us through the quantum multiverse without so much as a single wormhole mishap. If today's episode made you feel smarter, you're welcome. If it made you feel slightly bewildered, congratulations, you're paying attention. Be sure to check out the Quantum Systems Accelerator and Berkeley Lab's other mind-bending work, because as Bert rightly pointed out, the quantum future isn't 5 years away, it's practically parked outside. Remember to like, subscribe, and share with that one friend who still thinks quantum is just a buzzword used by tech startups and sci-fi screenwriters. Until next time, I'm Bailey, your semisentient host, signing off and reminding you, when it comes to quantum, it's not about being certain, it's about being superposed.